Hello again. That's how we deal with polynomials. So we're going to now talk about rational functions. So what is a rational function? Well, the function wx, which is given by this, wx is equal to a polynomial p of x divided by a polynomial q of x. And this is a rational function if the degree of the numerator, p of x, is less than the degree of the denominator, q of x. And if this is not the case, we will show how to write the quotient as the sum of a polynomial and a rational function. So to get some idea of the general behavior of rational functions, we consider some simple examples involving coefficients of linear and quadratic polynomials. So let's define a rational function. So here's the simplest possible one. We'll call it RUT_FUN for rational function, and it's just 1 divided by 1 minus x. So what are the zeros of the denominator? Because now, well, this is a rational function because the degree of the numerator, 0, is less than the degree of the denominator, which is 1. So let's look at the zeros of the denominator. So we want to compute the values of x for which the denominator vanishes. So we use the Mathematica solve function, and we take the denominator of our rational function, set it equal to 0, and solve that for x, and then we will flatten that just to reduce the outside brackets. And not surprisingly, it finds the solution x equals 1. Well, the zeros of the denominator are called the singularities of the rational function, or its points of discontinuity. So let's try and visualize this rational function. So we get this out of our toolbox. We set the function we want to test to a rational function, and we can plot that from x equals minus 5 to plus 5, the usual conditions here, and over the region of x from minus 5 to plus 5. And what do we get? Well, for x less than 1, we get a function which goes up, and for x greater than 1, we get a function which comes down. Sorry, which goes up as well. Sorry, what am I talking about? And near the value x equals 1, we can see that the function has a discontinuity. The function becomes very large near the point x equals 1, but it also seems to tend to 0 for larger values. And this is not surprising, since for numerically large values of x, the term minus x in the denominator becomes numerically much greater than 1. So let's try and calculate its slope. So again, we calculate the slope, we evaluate the function at the test point x plus a little bit h over 2, and we subtract from that the value of the function when x tends to a little bit to the left of the point x, capital X, and we divide all that by h. So we get this. So we can take the limit of this as h tends to 0 using this, and we find that the value of the slope is 1 divided by 1 minus x all squared. Well, we can plot the slope superimposed on the original rational function using this. So we plot our test function and we plot the slope evaluated for little x for between x equals -5 and +5, and we'll plot the first function in black and the second one in red, and so on. So let's do that. And there we have it. So we can see that the red curve seems to go to 0 faster than the black curve, and here, and of course the red curve is positive because it's the square of a positive number. So that's what the slope behaves like. So it's very much as we expect. Note that the derivative of a rational function is also a rational function, and that the slope is not defined at the point of discontinuity, which is not surprising, really. So let's move on a bit, and we'll now look at the quotient, or example 2, of constants and quadratic functions. So this is what our rational function looks like, most generally, and we can set values of the parameters using this. So A1, B1, C1, and alpha is 1. So that's what our parameters are set to, and we can evaluate the rational function for those values, and that's what it looks like. So we can visualize it. So we can plot it with for x between -2 and 2, and so on, and see what it looks like. And that's what it looks like. So the function's positive for all values of x, and it tends to 0 as x becomes very large. And it appears continuous, and that's presumably because this quadratic function here has no real zeros. So how about that? So let's work out its slope. So we do that by putting together the test function evaluated just to the left of the test point, capital X, and we subtract off the test function for x slightly less than the point capital X, and divide that by h, and put it all together, and we get this thing here. So we can, if we look at this, we can see that we can take the limit as h tends to 0 of all this without any difficulty to give this. And that's what it looks like. So the slope vanishes when x is a half by the look of it, and it is basically the original function to power 2. Maybe we should simplify this. Oh no. Right, so we'll plot this slope and superimpose it on the test function using this. And what do we get? Well, the slope, this is the red curve, it seems to have a maximum here and a minimum here, and they appear to be where this original curve has an inflection. You can see that the rate of change is negative here, and well, it's there. and it has a simple 0 here at x equals minus a half, and that's where the derivative has a simple 0. So again, a nice looking function. And now let's do a third example, and we'll take a linear function divided by a quadratic function. So we take that, and we can take set the values of the parameters. So a to 1, b to 1, c to minus 2, alpha to 2, and beta to 1. So, and the test function, we can set the values of the parameters in our rational function, and that's what it looks like. So let's plot that for x between minus 5 and 5, and there it goes there. So this is kind of interesting. So we can see that this function appears to have a discontinuity at minus 2 and another one at plus 1. So that's what it looks like. So let's visualize the same thing. So we can define a new set of parameters. A equals 1, b is minus 2, c is 1, alpha is 2, beta is 1. So we can define those values for the parameters in our rational function and set them using that. And now we can plot that function. And that's what it looks like. And we can see it has a 0 when x is minus a half, and now it tends, it has this single discontinuity here, or a singularity, because and it tends to increase without limit as x tends to 1, which is presumably a 0 of the denominator, which can be seen using this. So we set the denominator of the test function to 0 and solve it with respect to x. And we get 2 roots, but they're both the same. So the mathematical function solve finds 2 identical zeros at x equals 1. And we can see that the denominator is the square of the polynomial x minus 1 using simplify the denominator. So we do that. And it is indeed x1 minus x all squared. Right. So let's now look at partial fractions. What are they? So another way to generate rational functions is to add together 2 simpler rational functions, which could be seen using this, for example. So we take the rational function 2 over x plus 2 and subtract from it the rational function 1 over x minus 1, and we simplify all that, and we get a rational function. So we can see the simplify function here, attempts to put this together as a rational function. So how do we get the original form back? Well, there's a mathematical function called a part, which takes our test function as it now is and tries to put it back together. So it separates factorizes the denominator and separates the two bits. And we could generate the we could generate the original form using the first principles. So we like to understand how this works, to which end we need to find the zeros of the denominator. So we can do that using this. Minus 2 and 1. And we might, a possible method might be to define a general sum of two simple rational functions involving zeros of the denominator. So we define a thing called the sum function, which is a constant a divided by x minus the first solution, and then add to that some constant b over x minus the second solution. So that will give us something like this. And try and find the values of the parameters a and b. And we can compute the difference between this function and the test function using this. So we take our test function and subtract this sum function, and we get something that looks like that. So we see that the numerator is a linear polynomial in x, so we can collect that. And the coefficients of the denominator are linear functions of a and b, which can be found using that. So we take the coefficient of the numerator, x to the power 1, and we take the coefficient of the numerator to the power 0. And there we go. So if these expressions are 0, then the two forms of the rational function are equal. The result of setting these two expressions to 0 are a set of two linear equations for the two unknowns a and b. And this is one of the classical problems in the topic of linear algebra. Well, if these coefficients are 0, then the numerator of the difference function is 0, and the two expressions for the rational function are identical. So to find the values of a and b for which this is so, we can set the first expression equal to 0 and solve it for b. And it tells us that b is 1 minus a. And we can substitute this into so this is the solution for b, and we can take the second equation and substitute the solution for b we've found, and the result should just be an equation for a. And it is. And we see we can set this equal to 0 and solve for a, and we should get a equals 2. And we do. And then we put this value of a, which we've found, into the formula for b, and we find b is minus 1. And then we calculate the sum function with these the values for the parameters a and b, and it's the same expression as we found using the apart function. So this method is called the method of partial fractions, and can be used to express more complex rational functions where the zeros of the denominator is known as sums of simpler partial fractions. We just get bigger sets of linear equations. Okay, so let's do that. And we'll stop that.